All right, so in this example, we're again going to be looking at trying to identify a whole bunch of different types of remainders after we do a bunch of these little divisions. So in this case, we're going to be looking at these 4 different dividends. So in this case, I'm going to be looking at the numbers 14, 54, 179, as well as negative 36. And in this situation, I'm always going to be trying to divide by the exact same number. So in this case, I'm always going to be dividing by 5. And what's going to be neat about these examples, and this is a little bit of a spoiler alert, is that they actually share a very special property. And that property is that although they look very different from the initial kind of onset, they all actually have the exact same remainder when I do this division by 5. In this case, they're all actually going to have a remainder of 4. And we're going to use this example to kind of springboard our next conversation. It's going to be this idea that numbers that are all actually going to have the exact same remainder when I do this division by something in particular are all going to be lumped in this kind of big set or some really big kind of class in this case. In this case, I'm going to refer to these types of numbers as being congruent. So that's going to be a new piece of terminology as well as a new symbol. So they're going to be congruent to something. And in this case, they are congruent to 4 modulo 5. So that 5 is going to reference what the thing is dividing by, and that thing that I'm going to be congruent to is actually going to be indicating that little remainder that occurs as I go. So that's a little bit of where we're going to be going. We're going to now practice just a little bit of actually doing this division process to see this remainder come into play. So in this case, I'm free to choose whatever one I want to start with. So let's just say I start with, 54. It's a little bit more interesting than the 14, but kind of gets the job done on where we want to go. So we actually have 2 different ways to attack this thing. The first of which is the kind of old school, elementary school, long division side of things. So let's do that one first just to kind of believe that the remainder should be 4. And then after that, we'll go back and actually apply this kind of slightly more fancy formula to see this remainder as well as this quotient. Okay. So old school way, just to see if I can actually remember some long division sometimes. So the idea is that 5 is going to go into that 5 once, and then a 1 times a 5 is a 5. Bring that down as a 0 and a 4. 5 does not go into that 4 at all, so there's going to be a 0 up there. And you can see that immediately I have what my quotient as well as my remainder end up having to be. So I wasn't lying to you initially by saying, hey, the remainder is going to be 4. At least for one of them, I see this remainder of 4 popping out. What I do have now is I'm going to have this expression that 54 kind of has this nice factorization, or at least this pseudo factorization, which is going to look like 5 times 10, in this case, plus this little remainder of 4. So that's the thing I'm really looking for. And we do actually have a slightly fancier notation for this thing. I kind of skimmed by it when we initially mentioned this division algorithm, but we do actually have this kind of A mod D notation to reference what that remainder is. Because it's kind of a lot of words to say, well, what is the remainder of 54 when I divide it by 5? It'd be easier to just have some nice expression that actually kicks out what that thing's going to be. So in this case, what I'm going to say is that 54, when I do this division by 5, so in this case I'm going to introduce this little word mod, which is going to come back in a little bit again. It's going to have kind of a double dipping effect. What's going to happen in this case is that this just kicks out a 4. So it's kind of this nice operator that eats in 2 different numbers, and it's always going to kick out what that remainder is. For those of you in the C programming world or various programming worlds, there are different ways to represent this mod. A lot of times programming words would have something that says 54 in this case with a 5, with the word mod out in front, which would kick out a 4. And I know a lot of languages, I think C included, is going to say something like a 54 and then a percent symbol with the 5 would kick out a 4. So there are a couple different ways to actually represent what that kind of remainder is going to be in a slightly nicer syntax, but at the end of the day, what I really care about is what is that number, a little less of some of the kind of gutsy different computing syntaxes for these things. I'll let your computer science faculty really take that on kind of after we explore a whole bunch of these properties. So the other way that I could actually go ahead and find that number is going to be trying to use that little code that we had before, kind of what are the steps that actually gives me this output. So the way that we can do that is we can actually identify what that quotient is going to be. So the quotient in this case is going to be that 54 divided by the 5, and then I want to take the floor of this thing. Well, 54 divided by 5 is going to be something like a 10.8. And in this case, if I take the floor of 10.8, it's just going to kick out a 10. So in this case, my remainder is easy enough to obtain. All I'm going to do is take my initial number, which in this case is 54, minus my divisor, which in this case is 5, multiplied by that floor of 10.8. And I'm just going to write this out one more time just so you kind of see all of the pieces come together. So a 54 minus a 5 times a 10, in this case, you can easily see that that's going to kick out a 4. At the end of the day, this is probably a little bit more work, but this is actually something that's easy to code into a computer. It's just one line of code. It's just, okay, what is your remainder? It's just going to be your initial number minus the divisor multiplied by the floor of that quotient. So at the end of the day, you see that this remainder is also going to be a 4. What's nice about this is that that approach actually works really nice once we start diving into, let's say, some negative numbers. So in this case, if I wanted to find the remainder when I take negative 36 and I divide it by 5. Well, one of ways you can kind of go back to the elementary approach where you have to take 36 divided by 5, but then you got to deal with all these little negative signs, and that becomes somewhat annoying to work with. What I can do, though, is I can attack it with this kind of slightly nicer formulaic approach. So in this case, if I wanted to find the quotient, well, all I'm going to do is take negative 36 divided by 5, and I'm going to take the floor of that thing. If I take negative 36 divided by 5, which is a really poorly drawn 5, what's going to happen is that this kicks out a negative 7.2. And if I round this thing down, and here's the big caveat, is that it's tricky when you start rounding things when you're in the negative direction. This thing rounds down to negative 8. It does not round to negative 7 because that's a larger number than negative 7.2. So I want to round down. Okay, so there's my quotient of negative 8. So now if I want to think about what is my remainder, well, it's going to be my initial number, which is negative 36, minus my divisor, which in this case is 5, multiplied by this quotient. And I'm going to write it out kind of in that super longhand, what the formula actually looks like. So in this case, negative 36 minus this 5, and I know that that floor expression evaluates to negative 8. And at the end of the day, this is negative 36 plus 40, which is going to kick out a 4, which is what I thought it was supposed to do. The idea is that I'm going to have negative 36 is going to spit out a 5 times a negative 8 plus a 4. So my remainder in this case is this 4. And if I want to write this with this kind of fancy mod notation, this is going to be, well, what is negative 36 divided by 5? What is its remainder? So negative 36 mod 5, in this case, is going to kick out a 4. For those of you working in Sage, this is going to look like mod of negative 36 with the 5 is going to kick out a 4. And for those of you in the computer sciencey kind of C world, this is going to be negative 36 parenthesis, or this kind of percentage symbol, I should say, with a 5, which kicks out a 4 as well. So I'll let you check the other two examples, the 14 and the 179. You can kind of see them checked out here as well, this 14 and 179. In all of these cases, you can see that my remainder is constantly going to kick out a 4 over and over and over and over again. So what I'm going to say is I'm going to say that these numbers are all very similar, but they're only similar when I'm talking about this division by 5. So in this case, I'm going to say that these things are all going to be congruent, so that's going to be the new word, congruent to 4 modulo 5. So the 5 is going to be the thing that I'm dividing by, the 4 is actually going to be the remainder that occurs. So that's going to be this new definition. This is just kind of generalizing this away from just 5s and 11s and whatever we've currently been working with into this really nice kind of letter world. So in this case, if you give me two different numbers, so in this case A and B, I'm going to say that A is going to be congruent to B. So in some sense, they're going to be similar or connected. And they're going to be connected in this case when I do this division by n. So n is going to be some other number that I'm going to deal with. So A and B are going to be congruent modulo n if there exists some integer k. So in this case, it looks very similar to kind of the even-odd definition. If there exists some integer k such that that A can be represented as this n times k plus b. So the idea is that it's going to be some addition more than some nice multiple of that value n. In this case, we have exactly that back in this world of kind of looking at 14 or any of those numbers modulo 5. So we saw that 14 is going to be congruent to 4 mod 5. And the reason for this is that there exists some number, in this case that number happens to be 2, such that 2 times 5 plus 4 is going to kick out a 14. So in that case, I have that 14 is going to be congruent to 4 mod 5. We also have a few other examples of what 14 happens to be congruent to. If I look at 14 modulo 2, so in this case, what I want to start seeing is what happens to my remainder when I divide by 2. Well, in this case, it's kind of nice because I know that 14 is actually a nice even number, and if I divide by 2, I should not see a remainder, and that's exactly what happens in this case. 14 is going to be congruent to 0 mod 2. And we can also see that that works with the formula up above. If I take 14, and if I decompose it as a 2 times a 7, so there exists some k, in this case that k being 7, such that 2 times 7 equals 14. So the remainder is 0. We also can push this idea to other numbers as well. If I look at 14 modulo 3, well, what's going to occur in this case is if I take 14 and if I divide that thing by 3, what's going to happen is that I'm going to pick up a remainder of 2. And the reason for that is because I know that 14 is not a very nice divisor of 3 in this case. It doesn't work out perfectly, but it's close in a sense. I can see that there's a 12 just a little bit below 14. So if I can write this 12 as a 3 times a 4, it's just going to be 2 more than the nearest multiple, of 3 in this case. So in that case, it's going to be 12, and I just add 2 more. Likewise, if I start to look at 14 mod 4, well, what I want to think about is I again can springboard this off of this idea of, well, I know that a 12 can be made with this 4 because 4 times 3 is 12, and then I'm going to add 2 to it. So in this case, I again see this kind of modulo, it's going to be 14 is going to be congruent to 2 modulo 4. So the idea is that you can change up what your moduli are in each of these cases, and it's going to have an effect on actually what happens to this congruence world. So 14 is not always going to be the exact same thing. When I change the different moduli, the numbers are all going to change as well. And there's going to be a whole bunch of different types of theory on what these types of things actually tell us about certain types of numbers. You can kind of see already that this notion of being congruent to 0 mod 2 is going to lead into this world of actually being an even number. And if you look at this definition up above, actually, you can kind of see where that all comes into play. If I replace this n with a 2, you can see that I'm going to have very similar formulas to what I had in the odd and even world. And all that I'm doing in this case is I'm extending this idea so I have different types of multiples that are not simply just 2's. I can look at these kind of, well, how close am I to a near multiple of 5, or a multiple of 7, or a multiple of 14, or whatever I want it to be in this case. I can cycle through whatever I want to. So that's kind of the early world of this congruent stuff. If you really wanted to push this idea, you can start to see there are different things that occur as well. So one of the nice things is that 14, 54, and 179, they all happen to kick out a 4 modulo 5. But if I start looking at them modulo 2, well, obviously they're no longer going to constantly kick out the same stuff because 14 and 54 are even, so they're going to kick out 0's mod 2, whereas 179 is odd, so it's going to kick out a 1. So you can start to see that even though they're all equal at this stage, once I start switching levels, these things are going to break down very quickly. And you can see that sometimes they'll all come back again, other times they'll flip-flop around and things like that. So I ask you to just go back and double check to see if you can actually compute those things. See if you can actually identify that 52 is in fact going to be 2 mod 4. The idea is that you have to divide 54 by 4 and then see what the remainder is going to be.